Hey guys, I did actually have you read this section, and that was our assignment for yesterday, but I didn't want to go on from it without having at least one little talk about it and clarify a few things that I think are going to be important moving into the original stuff I wanted to talk about. So we have this idea of thermal energy that a lot of times people get confused with temperature, and they want them to be the same thing. And they are very, very related, but they are not the same thing. Okay, so thermal energy is the total energy of the particles of the substance. Okay, so it kind of has three things that would affect how much thermal energy they are. It's related to the speed of the particles, the state of matter they are in, and how many particles do you have. Okay, so all three of those would affect how much thermal energy is in those particles. Okay, so I have the three examples to kind of point out the three things here. And if I was going to number these, I guess I numbered these 1, 2, 3. And as we go through, let's kind of assign which one we're talking about here. Okay, so example 1, 100 grams of water as a vapor has more thermal energy than 100 grams of water as a liquid. So even if they're same temperature, same mass, vapor has more energy. So this would be the state of matter one. Okay, so solids have the least amount of energy, liquids have middle, and gases or vapors have the most. And again, I should have probably added, at a certain temperature. This would be like at 32 degrees Fahrenheit. Okay, because at 32 degrees Fahrenheit, it could be either. It could be either a liquid or a vapor. But the molecules that are in a vapor, if you had 100 grams of them, would have more thermal energy than as a liquid. All right, so example 2. Same mass of water, 100 grams, 100 grams. This time they're both liquid, but this one is 50 degrees Fahrenheit versus 40 degrees Fahrenheit. Okay, so would that be the speed of the particles, or how many there are? Temperature is speed. Okay, and then our third example, 100 grams of liquid water, 50 degrees Fahrenheit, versus 50 grams of liquid water at 50. So this time the same state of matter, they're both liquids, same temperature, they're both 50 degrees Fahrenheit, but this one has more molecules because it has more mass. So that would be kind of our third example, is pointing out that one. So we have these kind of three factors that all kind of can influence thermal energy. And unless you want to go in and do a bunch of really exciting math, we're going to move on just saying all else being the same, gas has more energy than a liquid has more energy than a solid. And then start over. All else being the same, higher temperatures have more thermal energy than lower temperatures. Or step 3, all else being the same, more mass has more thermal energy than less mass. Okay, when we're talking about temperature, we're zeroing in just on that average speed of the particles. So this is just one facet of thermal energy. Okay, but as a rule, and this is kind of pulled out of this section, the parts that I really think we need to kind of have figured out before we go into the stuff I was going to dive into. Heat always flows from warmer things towards colder things. Okay, cold is not a thing. Cold is just the absence of heat. Okay, just like dark isn't really a thing. Dark is just if there's no light, then it's dark. If there's no heat or less heat, then it's cold. Okay, so when you touch something, it feels hot to you because the heat is moving into your relatively colder hand. Okay, the opposite is true. If you touch something and it feels cold, heat is traveling from your warmer hand to the relatively colder thing. Okay, eventually though, the heat is going to move from the warmer thing, leave the warmer thing, go to the colder thing. So the warmer thing's going to be getting colder, the colder thing's going to be getting warmer until they reach the same temperature. And that's thermal equilibrium. So if you think about something that usually feels cold, maybe like a wall. Okay, if you touch a wall at first, it feels cold, but if you kept your hand there for like minutes and minutes, it would stop feeling cold, okay, because you have increased its temperature to match your hand. You would have reached a thermal equilibrium at that point. And then we also have this concept that as particles move faster, they need more space. Okay, you can always kind of think of this just like with people, right? If I had, think about in the science room, if I wanted to, I could probably fit 150 people in there. Gosh, it would be terrible though, right? You're shoulder to shoulder. If you wanted to move fast, go for running, you couldn't do it in that room with that many people, right? You couldn't possibly because there's too many people in there. If you're going to start moving faster, you need more space. And the same is true for individual particles and molecules. So the faster things move, their temperature is going up, they need more space, and the material expands. If you ever walked across a bridge, okay, you might see, if you look down, a strip that might look, I'm not going to make a very good one here, might look something like that. So like this would be the scale of like a human being. That's probably bad. But these would be expansion joints, so that in the summertime when the bridge molecules are moving faster and they need more space, the bridge doesn't buckle. What happens is these little gaps get filled in. So thermal expansion, it's a thing. It makes a difference. Okay, and the last thing from this little mini prequel is talking about temperature. Yes, we all love Fahrenheit because we're American, but it's not a grayscale. What it was based on was pretty arbitrary and strangely chosen. But anyway, you know my feelings on the subject. Fahrenheit is only used in the U.S. and a spackling of islands in the Caribbean, like Puerto Rico, I think the Maldives, Guam, a few places, but that's like it. Okay, and you know, Celsius is much more widely used throughout the world, and each degree is nearly double as 9/5 the size of a Fahrenheit degree, and you'll see that come back and haunt us in a second here. So, you know, if you're like, okay, so it's 60 degrees outside, and later this afternoon it will be 70, a difference of 10 degrees. Okay, so 10 degrees change in Fahrenheit is going to be more like 5 degrees of a change in Celsius. Each degree is larger. Okay, and Kelvin is the best for science, and we're going to have a long discussion about why Kelvin is the best for science. Maybe today. But in ordinary life, it's not that useful because every single temperature that you would ever use would be like in the 200s. And so it just seems a little bit cumbersome in real life, but for scientific purposes, it is absolutely the best. Here are our conversion formulas. So there's that 9/5, right? So we have to do the 9/5 or /5/9, depending on which way we're converting, to make up for the difference in degree size. Okay, and then we also have to either add 32 or subtract from 32 to get back to the same baseline, right? The freezing temperature of water is 32 in Fahrenheit and 0 in Kelvin. So we have to kind of cancel out that difference and also factor in the difference in the size of each degree. Okay, and then these two are conveniently, each degree is the same size, so we don't have to do anything too fancy, just add 273 to whatever. Okay, so I think I just want to talk through that concept development page. It's going to be one of those kind of unfortunate things where I wish there was a few more questions involved in this, and I don't think I can really have you do it. But I'll try to talk it through and, you know, add emotion and hopefully make it somewhat interesting. So we're saying plot the data in table 1 on the graph. So it says when the temperature, and we're in Celsius here, when the temperature is 0, some amount of air, so we're looking at this apparatus here, some amount of air has a volume of 50 milliliters. So I go 0, 50, there's my dot. At 25 degrees, it has a volume of 55 milliliters. So about right there. At 50 degrees, it has a volume of 60. At 75, it's 65. And at 100, it's up to 70. Alright, so I'm going to try to connect these. Looks like they're in a nice straight line. Okay, so we see this relationship. It's a nice straight line path. There's no reason for us to believe that if we went into the negative temperatures, that straight line would continue, right? So, if I grab a piece of paper to use as a straight edge, let's see what we can do here. Okay, so would go about like that. I didn't do great, but I did okay. So it says extrapolate, extend. So I would say that looks maybe like negative 210 or something. I'll tell you, that's not very good. I think my graph probably should have gone maybe more like over here, but that's okay. So let's think about this, okay? So we said particles that are warmer need more space. That makes sense. They're moving faster, they need more space. So it makes sense that our graph is kind of like this. As the temperature goes up, they need more space, okay? But, okay, does it make sense that we have any temperatures less than 0? All right, we said temperature is this concept of how fast are the particles moving. Okay, so with that in mind, with temperature as a measure of speed, okay, so using this idea, when the speed is 0, the temperature should be what? 0, right? They should go together. When the speed stops, the temperature should be 0. But you see, we have these temperatures that get less and less and less than 0, and it's not that the particles are moving backwards. It's that our temperature scale isn't very good. But we have this theoretical spot where they would stop moving, and it's negative 273. So my graph, like I said, was off by quite a bit. But let's think about this. So here's Kelvin. Okay, here's that same graph in the Kelvin scale. So I still have volume and I still have temperature. But now, when they get slow enough that they don't need any space, the temperature is also at 0. So this idea that of temperature as a measure of speed actually holds up. Because when the speed is 0, the temperature is also 0. Okay? And, you know, yes, we could never actually squeeze particles until their volume is 0, but we're, working off the idea that volume corresponds to temperature. So the colder it is, the less space it takes up. So, the answer, yes. So the idea of absolute 0 is this concept that 0 actually means 0. 0 actually means, like, 0 temperature actually would correspond to 0 speed. Okay? So, with that, I feel like I talked through that pretty extensively, but let's just kind of talk through this very first section here, and we'll dive into the first law of thermodynamics first thing tomorrow. So, idea of absolute 0. As the thermal motion of atoms in a substance approaches 0, the kinetic energy, which is a measure of speed, which is a measure of temperature, reaches 0, and the temperature reaches some lower limit. As we study how all this works, that's thermodynamics. Okay, absolute 0. Okay, absolute means actually, really, truly. So this is that idea of an actual 0, an actual temperature where the speed of the particles is 0. Okay, And absolute zero is 0 Kelvin, or negative 273, and there's some decimal at the end of that, but we'll just go with negative 273 degrees Celsius. And again, they're emphasizing that same deal. Those degrees are the same size. So if I went from 0 Kelvin to 1 Kelvin, that's the difference of 1 degree. That's the same as going from negative 273 to negative 272. It's an increase of 1 degree. Okay, but an increase in 1 degree on either of these would be an increase in almost 2 degrees on the Fahrenheit scale. So it's kind of weird. And here's our kind of baselines here for ice, for water, I should say. The melting temperature of water is 0 Celsius, or 273 Kelvin. And the boiling temperature, just add 100 to each, 100 Celsius or 373, 100 degrees difference between these two, 100 degrees difference between these two, because the degree of each is the same size. Okay, so I feel a little better moving into the rest of this section with that review. Hopefully it wasn't too boring for you. Either way, we will endure. Thanks for listening and watching. All right, bye.